Yes, here we are. This is a new discussion, a new roundtable. As Alexander was saying, we'll be talking about simulation, artificial intelligence, machine learning, revolving around energy. So let me welcome my four guests who will be joining me on the rostrum in just a second. Welcome to you. Round of applause, yeah? Wouldn't be too bad. It's the morning, we need to wake ourselves up a little bit. Thanks very much. All right. So, from left to right, let me start with you. Patricia Prod'Homme, you are R&D Coordination Innovation Manager. Perhaps you can clarify what your job involves. I'm responsible for R&D coordination, innovation, sustainable development at TotalEnergies. So those who may not have picked that up, yes, coordination and innovation. Right, Anthony Credoz, you are responsible for a very interesting topic. You're project leader on Earth observation and artificial intelligence. We'll be talking about that, straddling Paris-Saclay and Pau in the south of France. Thank you very much. And Maxime Pallud, welcome to you. You are an R&D computational physics project leader. What does that involve? Well, I'm responsible for R&D projects involving data, artificial intelligence, and digital simulation. So very much at the heart of our panel's interest today. And here we have Toufic Abboud, Praise Pascal Prize winner of 2005, CEO of IMACS, which is present on this Polytechnic campus. So as I said in my introduction, we'll be looking at these technologies that are more and more mastered, particularly deep learning, machine learning, that are sitting behind what's described as artificial intelligence, devoted to the energy sector in this particular instance. So I have a question for you, Patricia Prod'Homme. Of course, we know about accelerated international conflicts in Europe that are much more present, that also revolving around energy matters and climate matters. And so, obviously, TotalEnergies' vocation that has renamed itself by introducing renewables into its name. But since you come from TotalEnergies, renewables, and that business, what is all about then this energy and climate matter all about for your company? Well, it's crucial for the 21st century, and we are multi-energy service providers, so we're at the heart of all this because our job is to give access to a growing population, access to energy, while also thinking about the environment. So obviously this involves a number of ambitions, carbon neutrality across all our businesses around the world between now and 2050. It also means providing support to our customers to help them reduce their carbon intensity. And it goes beyond carbon as well, by the way, because we want to have a sustainable energy production which sits well with the environment. So our challenge, obviously, is to be among the top 5 worldwide for producing renewable energy with 100 gigawatt installed base. So with that particular point in mind, R&D, digital, has pride of place, has a genuine role to drive us into that ranking and explains our presence here at Paris-Saclay. So decarbonizing, of course, is crucial for all companies. They have to reduce their carbon emissions as quickly as possible. So the renewables market, which is part and parcel of this zero carbon objective, is pretty competitive, isn't it, that market? I suppose that's good news. That's good news, because obviously, it means that we're actioning this transition. And how then do you support the growth in TotalEnergies that we're seeing in that market, particularly with R&D lying in the engine room of this competitiveness? Well, R&D is crucial, and this is why we allocate sizable budget to renewables. It weighs in for pretty much half of the group's global R&D expenditure, so it's a crucial facet of what we do. Another question, and digital. How does that get involved? Digital in its broadest sense, all these techniques involving digital to transform our societies, our companies, the sectors, the business sectors. Can you give us an inkling into the role of digital in the renewable field? Yes, energy transition will involve a change in our energy mix, energy portfolio, greater complexity in managing energy flows, and even flows between energy consumption and energy production, intermittent sometimes with renewables. And so managing something that's more complex with digital, because of its ability to model very complex phenomena, and to provide a simulation and to analyze and predict, forecast future trends. It can adapt itself better to intermittent production of electricity over the grid. And no doubt other people on the rostrum can talk about that better than I, because it's their specific field. But another aspect for digital is to help us making decisions about devising, building new power stations, because digital basically gives us a potential to combine very different sets of data. It could be image data, it could be, also thinking about different sources of this energy and how that can be modeled, wind or sun. And Anthony and Maxime perhaps can tell us how we can do just that. I don't know. So R&D really has pride of place, along with digital. All right, then let's talk about this project, Anthony, that was exhibited here, Earth observation and artificial intelligence. So no doubt this is an application that is involved with observing the Earth, uses machine learning, or deep learning possibly. So tell us then, in a word, what this project consists in. Well, it's called Demeter. Demeter, right, okay. Yes, it wants to make Earth observation readily available to everybody, thanks to artificial intelligence, made available to everybody within the company. It's part of our global ambitions for sustainable development, for carbon storage, and to reduce our CO2 emissions. Now, the idea today is to make sure that we have a web app where our engineers, our researchers, can retrieve metrics, pictures, particularly about looking at potential offshore wind farm sites or photovoltaic sites, thanks to this app. So the fact that we can get data instantaneously, which is raw data, so it's not easy necessarily to swim through if you're a neophyte. All right, so if I'm following what you're saying, then you're saying that Demeter involves finding sites, particular locations, geographical locations, where you're going to be optimizing the performance of a potential, let's say, wind farm or what have you. Yes, that's right. We're using this ocean of data that is generally free of charge, or it may involve also solutions which come with a fee. But we want to use that in conjunction with our AI to interpret that data and, to use that to think about finding the best site for wind farms or solar farms, and then track the production of these sites. And two avenues of research are involved with that, for example, with looking at cloud behavior, about sun's rays, looking also about the wind speed offshore, and those are two research fields. So you retrieve through Demeter this satellite imagery. With that, then you're tracking real time, any machine or any individual that's operating a site, a electricity production site. Is that right? Yes, well, it's not operational yet, but this is an avenue of research that we want to embark upon. And this is what Patricia was talking about earlier on, about, decision-making assistance tools for the future. Right, we're talking about Earth observation. So this is satellite imagery, some which will be available to everybody. So perhaps that's a shoe-in to open data. How is that data used today? What type of data are we talking about to best use that data? Well, when you're looking at a remote detection, you have to think about retrieving the data and downloading the picture. It might take days or weeks, and then interpreting the picture. Now, of course, there's lots of data, but there is databases that are available. Yes, that's right, free. The European Space Agency, NASA, offers free data pools. But you have to think about how you can handle this data and possibly fine-tune it, and then how to interpret it for our operational staff, hence the importance of AI, with scenarios that are built by algorithms. So you're going to be able to use those data sets in relation to a specific target. Is that right? To summarize, that's right. I mean, the bulk of the work in AI is preparing the sample, yeah? So that requires a physical understanding of the data, and then obviously the ability to operate as a data scientist, but also you need agronomists, you need other scientists to get involved. Now, before moving on to your neighbor, let's stay with Demeter a little bit and where it comes from. It was a research project at its inception, wasn't it? Yes, that's right. At its inception, it was called Naomi, which went from 2014 to 2019 it was in conjunction with a partnership with Owner and Total, looking at core business energy for Total at the time. And at the time, we realized that this data boom that we saw meant that everybody was going to be able to access that data. And that was maybe going to introduce a paradigm shift. All this obviously was backed onto AI. So we said to ourselves, right, we're going to continue working with Onera at Toulouse and Palaiseau, just around the corner, Toulouse in the south of France, but also we've got the dynamic meteorological site in Paris, Paris-Saclay, here, where we speak at Polytechnique. We've also opened up to other teams with whom we work, Google Cloud, for example, and foreign universities, Toronto, based in Brazil. All right, thanks very much for those clarifications. Perhaps now we can think about how offshore wind farms operate, which is part and parcel of TotalEnergies' operations with respect to its renewable division. Maxime, you're responsible for R&D computational physics. You'll tell us, no doubt, what that involves in greater detail. But thinking about these wind farms, obviously this can't be dreamed up overnight. It's not a magic wand that's waved and hey presto, they appear. But of course, when they do appear, they need to be in a windy area. How do you set them up then? And what knowledge base are used to build these wind farms? Well, the technology has changed considerably. They're very sophisticated items now. They're also land-based. They're close to people's homes. Of course, it's more straightforward to have them land-based. But you also want to, because of their proximity to where people live, you want to make sure that don't produce noise pollution. There are lots of topographical constraints. You will have seen, no doubt, that wind farms are alongside motorways. But we also set them up in the sea. And they have based on nominal power, they're going to be producing 60% of its capacity. It's quite a lot, actually, when they're installed in the sea, because that does bring with it certain constraints. So you have to set them up in the first place. You have to take them to the site where they'll be built, and then you have to erect them. And in the North Sea, in the English Channel, you can put them on the seabed at 70 meters below the sea level. But in deeper levels, you're going to set up wind farms on floating structures because you can't reach the seabed. These structures will be anchored in different ways to the seabed so they don't drift. Now, this will involve undersea, subsea cables so that they're hooked up also with the terrestrial grid. So all these new complex systems, it's all tailor-based, really, particularly for these floating installations. And we need computer-assisted decision-making tools. Artificial intelligence is involved in there, for example, to help a research unit to really have these tools that help them make the right decision. And TotalEnergies invests considerably in land, but also sea-based wind farms. We have 10 gigawatt installed base, which is considerable. We want to add 30 gigawatt to that between now and 2030 for the sea arm. Now, simulation tools, we find in your job title, computational physics. So it's all about physics, isn't it? We can talk about sea conditions. That requires a certain set of knowledge. But at the end of the day, it's technology that is used in conjunction with physics, what man is able to manage or not, for that matter. Yes, so we set up these wind farms on the sea using digital models, on optimizing models, which will help us grapple with locating these wind farms optimally. We're going to try and make sure that these wind farms are close together to optimize the production. That means putting more and bigger wind farms, but of course that may involve them polluting each other's ability to produce electricity. So we're going to try to position these wind farms, knowing about wind behavior in a particular area. We'll have statistics about wind behavior in a particular area. So we're going to locate these wind farms in the optimal area, and we do that by using AI and AI models. So there are lots of settings. We have to think about positioning the wind farm in the right direction to capture the wind optimally. And there was a doctoral thesis done on that very point. Reinforcement learning as well, because we need to make sure that we can really track what's going on to optimize the yield of electricity from these installations. So this requires new disciplines, no doubt? Yeah, absolutely, very recent. That's right, yeah. You know, everything that's built on AI, TotalEnergies is very much in the vanguard, but we also need more mainstream straight-laced equations, mathematical equations, and it's really finding the right balance between the vanguard and straight-laced mainstream equations that it's all about. And for devising the wind farms, we had these floating installations I mentioned. These are very complex. It's too expensive, really, and so it's not profitable enough. We need to make sure that we have the best cost of energy, better cost of energy to be more competitive based on what we see on land. But you know, innovation-wise, we're very much ahead, and we've got an experience of working offshore. So these sea-based installations are anchored to the seabed. We can optimize that anchorage. We can develop new anchorage systems for very deep-sea structures. So all these aspects raises lots of questions, and this means that we need multi-physical analytics. We need to think about the wind, the sea behavior, etc. We need high-performance computing. And we also, therefore, need to obviously use AI to improve the flow of results and data crunching. So lots of scope for innovation in that field. And this is why we need to draw on young researchers, particularly young researchers. We're fleshing out our teams considerably to pick up on our ambitious targets and using Paris-Saclay partnerships as well, hence our presence here. All right, then, the energy transition, renewables of today, not necessarily the future. Of course, this involves batteries. We need to store electricity. This because we have intermittent electricity production, particularly from the wind farms, not only from the wind farms. And this is really what I'd like to turn to now. Toufic Abboud, you won the Blaise Pascal 2005 award. You work at IMACS. Tell us about IMACS, what it involves, before talking about batteries proper. Well, IMACS is a spin-off from the applied computer division here at Polytechnique, involved in developing innovative digital methods, scientific computation software to help industry. A small team devoted to collaborative research projects and multidisciplinary as well, which means that the simulation is successful ultimately. We work with Airbus, looking at reducing noise, for example, and we work with TotalEnergies currently, and its subsidiary, Smart, that's responsible for battery manufacturing. So these are examples of tangible collaboration. Talk about digital twins for batteries, for example. That's what we're involved in. And they're designed to reproduce very accurately the physical behavior of lithium-ion cells that are operating in load and offload cycles when they operate normally, but also when they go awry, or even for swift charging. So these digital twins are used to optimize mainstream batteries, but also to take us off towards new battery concepts without solvents or full solid batteries. So again, that's a breakthrough technology. Our approach is based on experimental approaches. We use physical equations that are sized to the matter at hand, using the properties of the materials, using massive IA machines capable of doing massive computations.
Okay, so your key expertise is in mathematics, obviously. But talking about this some more, talking about batteries some more, what's the use of mathematical simulation in an optimization process? Well, battery technologies have evolved quite a lot over the last 40 years, and now they're very innovative technologies. So the objective of a simulation is first to design digital models capable of reproducing the physical experiment. So first you start with equations from physics. You use digital analysis to make these equations discrete. You use fast and parallel algorithms. We implement them in an efficient way. We use huge machines to carry out these simulations. And once we have these simulations available, we need to validate them. So we'll have validations with experiments, either in operation, the post-mortem experiments. And it's once we have a reliable model that we can go further. So we look at microscopic level, what's going on in deterioration when a battery deteriorates, why that happens, how can it be avoided. And then we we can use these simulations to optimize design. So simulation allows us to go one step further as compared to just simple experiments, and it allows speeding up the innovation process and the design process for batteries, thanks to what we call virtual design. Okay, so we can imagine that the most important thing is to have these batteries last as long as possible. That's what we're looking for. And big giants pushing this market, we're all thinking about Elon Musk, but he's not the only one. So we're talking about batteries for EVs. What can your work contribute for a battery for EVs and for charging stations? Are there things happening at the moment? Well, one important aspect is fast charging, especially when you're on the motorway. And we know that fast charging can deteriorate the battery and reduce its lifetime. So by having a vision of what happens at microscopic level, and thanks to AI and calculation conducted by machine learning systems, and having substitution models that can go through smart system for the management of the battery life, simulation allows increasing the lifespan of a battery. Okay, we'll talk about quantum computing. I know that everybody's fascinated by that here, but are you using quantum computers with huge computation capability? No quantum technology so far. We're still using huge computation clusters as the one they have at Total. In order to achieve that, we need to have a large number of people working in different specialty. We have electrochemical specialists, mathematicians, physicists, computer people, HTC specialists, because when you use these machines, you need specialists. So you need lots of people working together. Okay, so that's still a field for exploration, and that's fascinating. Last words from you, Patricia Prod'Homme. Let's talk about Saclay. We didn't talk about this that much at the beginning, but how do you envisage continuing your cooperation with the ecosystem here? Well, we've been here for a long time, because we started with a team of LPICM here at Polytechnique. Then there was PVF, and this is an environment, an ecosystem, which is very interesting, and our historical presence here allows us setting up cooperations and generate value, because at the end of the day, digital technologies are important, but what's at the core of everything are human beings. We've talked about the number of people required to carry out a simulation. So it's thanks to the human assets that we can move forward and benefit from this wonderful ecosystem. Okay, so an ecosystem that needs to be comforted by the presence of large industries. Thank you all for having joined us on this set today. We were talking about green tech in the Spring 50, and the mic has been disconnected. Okay. Okay, sound is back. So Spring 50 is back. Green Tech was the first part of our spring competition, but now we'll have 5 other startups talking about digital technologies. Over to you, Alexandre.